Morning, students. Today we start analyzing the performance of the bridge rectifier. In our last two classes, we have analyzed the same performances of a half-wave rectifier and also a full-wave rectifier. Now let's see how the bridge rectifier works, right? Now, this is the diagram of a bridge rectifier that you already know. That there are four diodes and one single secondary of the transformer, and output is a full wave or rectified output, as in case of a full wave rectifier. And since the output is full wave rectifier, of course, most of the characteristics of a bridge rectifier will be same, but one or two may be different. We shall see now. Right now, we shall see. First is transform. We are always worried about the transformer because if you ask me precisely, if you go to buy these components in the market, you will find that in a rectifier, transformer is the costliest part. Diodes are available very cheap nowadays, so don't worry about the diodes. Here, the transformer is a single secondary transformer, as in case of half-wave rectifier. So you save money on the transformer, right? Second, next is we see what is the transformer secondary voltage needed. Transformer secondary voltage is only Vm by root 2 because the transformer secondary peak value is Vm. So Vm by root 2 is the transformer secondary voltage. Now, number of diodes, we need 4. In half-wave rectifier, we needed 1. In full-wave rectifier, we needed 2. And in bridge rectifier, we need 4. Next, peak inverse voltage. Peak inverse voltage is the maximum inverse voltage that falls across the diode. The peak inverse voltage of a half-wave rectifier was Vm, of a full-wave rectifier was 2 Vm, and for bridge rectifier, it is once again only Vm. Let us see this in case of a bridge rectifier. In case of a bridge rectifier, here, say this is the positive cycle. So this maximum value is Vm, and current starts from here, goes into this direction, then goes through the load, then goes from here, then from here, current goes back here. This is the path of the current. So this diode is reverse biased, right? Now, what is the maximum voltage here? Is the Vm, when the current is passing through here, the maximum voltage is Vm. Then other end of the diode is at the circuit common. So diode peak inverse voltage is once again Vm. But for your full wave rectifier, it was 2 Vm. So diode could be a little costlier. Then comes, this is a statement, output of this bridge rectifier is same full wave rectified output in case of a center tapped full wave rectifier. So VDC, VRMS, etc. also will be same because their values come from your integration and average. Still, just repeated once again, output DC voltage is VA2 Vm by pi, like in full wave rectifier. Output RMS voltage is Vm by root 2, like in full wave rectifier. Then ripple factor will be 0.483, like in full wave rectifier. Ripple frequency is 2F0. Form factor is 1.11. Efficiency is 81%. So overall, it appears to be a good rectifier. Only 4 diodes are needed. But as I told you earlier, that nowadays you can go in the electronics market, you can buy a single device with 4 rectifier diodes in one device. Anyway, then comes transformer utilization factor. Transformer utilization factor is here. Calculate what we calculate. We calculate DC power delivered to the load is VDC by RL. Power delivered is V square by RL. So what is the VA rating of the transformer? Is VA rating of the transformer is the RMS voltage Vm by root 2 multiplied by DC power DC multiplied by VC power is Vm by Vm square by 2 RL. Right? Now, here, so transformer utilization factor is this DC power, which is VDC square by RL multiplied by VA rating of the transformer is Vm square comes to the denominator now, divided by 2RL, which becomes 81%. Mind it, transformer utilization factor of half-wave rectifier was very poor, was some 28%. Right? Okay. Here, in the next slide, I have shown you a chart. If you can just visually remember this chart, it will be very useful to you. This is a half-wave rectifier, center tapped full wave rectifier, and a bridge rectifier. Transformer, half-wave rectifier, you need single secondary, center tap, you need double secondary center tapped, bridge, you need single. So here, the half-wave rectifier and bridge rectifier is transformer is easier and simpler transformer. Secondary RMS voltage is V, 2V, and V. Right? Of course, RMS voltage we are not much bothered. We are bothered about the DC output. Number of diodes is 1, 2, and 4. So double and 4 times costlier cost on the diode. Peak inverse voltage is half wave is Vm, bridge is also Vm. So the diode is, that means the bridge rectifier diode, although you need 4 diodes, but peak inverse voltage is only Vm. So it is not 4 times costly. V is what we are bothered about. What is the DC output? Because you have designed this rectifier to get DC. For VDC, for half-wave rectifier is Vm by pi. Center tap rectifier is 2 Vm by pi, double. Bridge rectifier is same. RMS voltage is this. We are not much bothered about this, but we are bothered about the ripple factor. Ripple factor is the AC component by DC component. Here, AC component is more than the DC component. The ratio is 1.21. And these two cases, it is AC component is about slightly less than half of the DC component. Ripple frequency is F0, and in these two cases, 2F0. You remember what difference does the ripple frequency makes? If the ripple frequency is more, the filtering of the AC component will be easier. Form factor is 1.57, 1.11, 1.1. Efficiency of the whole rectifier. Half-wave rectifier efficiency really very poor, only 40%. And other two, efficiency is good, 81%. Now, so far as the transformer utilization factor, that means how much the capacity of the transformer is used. Half-wave rectifier is very poor, 28.6%. Center tap is little more than double of that, 69.1%. But the transformer utilization factor of the bridge rectifier is very good, is 81%. So here we end the lesson of 3 different types of rectifiers, their performance factors, and a comparative study of their performances, right? In our next class, what we shall do, we shall actually design these rectifiers and see how they really work. We shall work on the actual rectifiers, right? So we end here today. Have a nice day.